Okay, thanks, Giannis. So today I'll talk about planning against a background of continuously changing time and resources, which, along with green issues, is one of my interests. Okay, so start with an outline. Oops, an outline of the talk. Derek, do you have my radio mouse there? Ah, here it is. Start with an outline of the talk. I'm going to introduce a motivating benchmark problem, and I just gave you, by accident, a little preview of that. This is intended to show you an example of where this kind of continuous change arises, and in particular, when continuous reasoning is interesting for planning. Because sometimes it's not interesting to reason explicitly about this kind of continuous behavior within the task planning framework. Sometimes it's possible to discretize everything out and you don't suffer too much in terms of the quality of the solution. But in other situations, it's very important to reason explicitly with some of the continuous behaviors of the problem. So when that is necessary, then some modeling issues arise, and I'm going to talk about some of those problems. And then I thought that it would be useful to do a sort of overview of some of the solution strategies that have been proposed in the literature for starting to look at this kind of problem. So I'm going to compare several different solution strategies and try to draw some connections between them so that we can see where the state of the art is in reasoning about continuous change. So I'll then finish up by saying something about the progress that's been made here and what are some of the remaining challenges for the community. Okay, so this is my benchmark problem. It's a kind of benchmark version of the sort of domain that Steve was talking about in his demo talk the other day. So coordination of AUVs or gliders in an ocean, a dynamic ocean environment. But I emphasize this is a benchmark version, and it can be coded up in our PDDL languages and used as an experimental basis. So that's what we'll do. But in this situation, you have two AUVs cooperating on a science mission in the ocean. And the mission that they have, in my example, is that they need to get an image taken of a science target deep down in the water. Because it's deep down in the water, it's dark. So a light has to be shone on the science target for the picture to be of sufficient quality. And if you shine the light from the same direction as the camera, then the problem is that the backscatter spoils the quality of the image. You just get, it's like taking a picture through fog. Okay, so what has to happen is you have to have one AUV coming in and shining the light from an angle, and the other AUV comes in and takes the picture. So it's a cooperating problem. And this is important because it means there's then coordination, temporal coordination of activity in this problem. So let's have a look at what a plan might look like. So it's temporally coordinated, they have to operate together. One comes in and shines the light, and the other one takes the picture. Okay, so that's the basic problem. However, there are some additional constraints, because as Steve was mentioning the other day, the ocean's highly dynamic. You've got currents, you've got tides, you've got all kinds of stuff happening, which means that it's a difficult environment for vehicles to navigate in. So in particular, you can't sequentialize the behaviors of these two AUVs, because if you have them perform in sequence, then the first AUV will get into position and shine the light, but by the time the second one arrives to take the image, the first one has sort of drifted away because of the currents, and then there isn't sufficient light to get a good quality picture. Okay, so what that means is that there's an interesting temporal coordination problem to get the two AUVs into their respective positions at roughly the same instant so that they can then go on and do their picture-taking activities. And this kind of temporal coordination, as you can see from the picture at the bottom, is a kind of organization of durative temporal activity in such a way that both AUVs terminate their navigation at the same moment. And that can be done using, for example, temporal windows that can model deadlines that the temporal coordination has to work with respect to. However, we also have some spatial constraints in the problem. So in particular, when the AUVs move through this dynamic environment, they're moving through sort of tubes of possible trajectories. And as Sebastian said the other day, if you've got vehicles navigating in a dynamic situation and you discretize their motion, then they'll never reach the goal. Right, so this is definitely a situation where continuous reasoning is required to get the AUVs properly into position. But that part of the reasoning, you would deal with that through motion planning, path planning techniques. That would not be something that you would fold into the representation of the task planning problem. So this is interesting now because you've got this path planning and task planning element to the problem, which I think those of you who are at the workshop on motion and task planning might be interested to see. This is one of those examples where you require both. Obviously, there are dangers of collision when these two things are operating within the same sort of small region of water, and the motion planning would be dealing with making sure that no collision occurred. So we now have a problem with continuous spatial and temporal dynamics, right, and discrete choices, because we had to decide on the organisation of our durative actions. So we have a hybrid problem here, but let's suppose that you have a really good geometric reasoning package from the roboticist to understand how to do the path planning, and you have figured out how you can call that, integrate it with your task planner. And then, as I said earlier, the temporal coordination can be managed through durative actions and temporal windows for ensuring that the activity terminates at the right moment. So currently it looks as though we can model this with the technology that we already have. But what you just saw there was the thing that makes this an interesting problem. It's that reasoning that's required to do the precise organisation of the picture-taking activity at the moment when the AUVs get into position. So it's like this. They get into position, and then there's the coordination of these two activities, illuminating the target and taking the picture. That's the bit where the challenge arises. This is where it's now necessary to do some careful reasoning, because you've got some additional constraints, such as, because of the drift in the ocean, illumination is deteriorating at some rate, let's say 20% per second. And then let's suppose that the image quality is dependent on that, because the image quality depends on the exposure time of the image, and the exposure rate is itself dependent on illumination. So now we've got a continuous interaction between the illumination and the exposure time, which means that if you're deciding how much time you can waste between the light coming on and the picture being taken, you need to know what that interaction is in order to decide how late you can possibly leave it before you click the shutter. Okay, so the picture-taking decisions introduce some continuous temporal reasoning that is more subtle than the reasoning that's required to navigate the rovers to their destinations by the same moment. So here's a schematic of what's going on. We have the light level deteriorating according to a simple linear function, so it's 20% per unit of time. And then we have a quality threshold for the image. So we must get an image of a certain quality. And what you can see in this example is that if you click the shutter the instant the light comes on, then you have no problem surpassing the quality threshold. You're definitely going to get a good quality image. But if you leave it even just a little amount of time, because of the nonlinear interaction between the illumination and the picture quality, the exposure rate, then you're going to risk underflowing the quality threshold. So you don't have to leave it very long, so it's quite tightly constrained. However, in the example as I've presented it so far, there is no constraint to stop the picture-taking AUV clicking the shutter as soon as the light comes on. Right, so there's no reason why not to just get the AUVs into position, turn on the light, click the shutter, and you're done. Problem is solved. And that's because in this situation, we only have a lower bound, which is the picture quality. We don't have any upper bound constraining any reasoning about when the picture-taking activity should be done. But it's easy to imagine additional constraints that supply that pressure, because it may be that the AUV with the camera is already committed to taking an image somewhere else or doing some other activities. And if we're in an oversubscription planning framework where it's a question of maximizing the science return and choosing whatever goals are going to allow the system to do that, then there could be this delicate reasoning will arise when the AUV is deciding whether it's whether it's possible to get into position in time to take a good quality image. So a simplified situation where this kind of bounds reasoning occurs is this one where, again, you've got something that's deteriorating according to some simple function, but then you've got, in this situation, you've got both a lower bound and an upper bound, and now there's some action that you could apply, a durative action, continuous effect action, that you can apply somewhere in that region between those bounds. And the question is, where do you start applying it so that the continuous change that it triggers doesn't cause you to exceed the upper bound of the problem? So there's the reasoning is, where do you start the action? Because if you start it too early, you'll exceed the upper bound. If you start it too late, you'll underflow the lower bound. So that's where it becomes interesting when you've got these two bounds in place. Okay, so in our example, we can model the interesting behavior that's going on using PDDL 2.1 actions. This is just the endpoint where the first AUV is turned into position and it starts the illumination. Notice that the illumination starts while the AUV is still turning. That's because, as I said, if it stops for a minute, then it's going to drift away, and by the time it turns the light on, it will already be too far away from the target. So it's going to sort of turn into position and illuminate. And similarly, the other rover has to AUV has to dive into position and then click the shutter whilst it's in position rather than when it's drifted away. So the way that we would model the actual interesting effects is, as soon as the illumination occurs, the light is at the maximum possible level, right? And then in PDDL 2.1, we can write this type of effect that says that immediately the drift rate starts to affect that continuous variable, which is the light level. And this looks like a differential equation. Don't think of it like that. Think of it as an update to a differential equation, because there might be other things that are affecting the same continuous variable concurrently. And what this allows us to do is concurrent continuous updates on the same continuous variables. So when we start that illuminate, we add that additional continuous effect. And when we end the illuminate, we remove that continuous effect. And similarly with the shoot action, when we start shooting, the exposure time is being increased by the exposure rate times the light level. And when we stop, then we take that out of the equation. So what we have here are updates being done incrementally, not by assignment, right? So we're adding in or removing the particular continuous effect that we've introduced or finished by the execution of those actions. And a common way to interleave durative actions has been to take the start and the end point of the durative action separately, and then when they occur in a plan, you enforce the invariance of the action as constraints that must be met by any plan in which those two endpoints occur. And that's the solution to doing concurrent interleaving of temporal activities that we implemented in LPGP in 2003. It's also used by other people since, but when I refer later to LPGP, it's really this translation of the temporal durative actions down into these endpoints that I'm talking about. Okay, so it's dark in the ocean, right? But what I've presented to you so far, I haven't given you any reason to think that this is a planning problem. I mean, we've seen all kinds of numeric interactions going on, but what we haven't seen is any real combinatorial choice in the problem. Okay, so I'm going to assert right now that for a planning problem, for a problem to be an interesting planning problem, there must be this combinatorial choice, so discrete choices about activities, as well as all the other things that you might see in this kind of example and others. So how might combinatorial choice arise in the problem that we've been looking at? Because at the moment, right, you just get the AUVs into position, they do a bit of numerical reasoning about when to shine the light and click the shutter, and that, if that's all you had to do, you'd be better off, given the good technology that exists, coding that up as a numeric program and handing it off to Cplex to solve it. Right? So it only really becomes interesting when the combinatorial choice exists. So in our example, If you had a ship that could shine a big light beam down into the sea, that's an alternative way of lighting up the science targets that have to be illuminated. And now you've got a choice about whether you use that beam or whether you use a specific beam off one of the AUVs or indeed another beam off another AUV. Automatically, without really adding any more structure to the problem, you've got a bit of choice now about how you achieve one of the goals, which is to have sufficient light on the target for the image to be taken. Okay, I'm going to now talk about solution strategies, and I want to just start by mentioning two solution strategies that I'm not going to talk about further in this presentation, but they need to be mentioned. So I'm not going to talk about them further here because I'm going to concentrate on more recent work that's been done on looking at planning with continuous change. But these two, especially the first one, are really, core to this area because they were the first planners to really address this issue about how do you reason with this continuous behavior. And Zeno was done back in 1993 on top of the UCPOP partial order planning framework. And it was looking at the problem of how do you manage differential equations within this partial order planning framework. And the other one, OpTop, that was Drew McDermott's planner back in 2003, which is also looking at management of these continuous processes, but within a forward chaining framework. And the reason I'm not going to dwell on these further is because they're quite old technology now, so not exploiting the various opportunities that there are these days to exploit when you want to do that kind of reasoning. But it is important to remember that much of the inspiration for the kind of work that we do now in continuous planning comes from that background. And these are the ones that I am going to talk about. So I'm going to start by talking about Kong-Ming, which is the graph plan-based planner that uses a mixed integer linear programming tool. Then I'm going to talk about TMLPSAT, which is a SAT-based planner that uses a linear solver. And then Colin, which is our own forward search planner that uses a linear solver. And then I want to talk about UP Murphy, which is a model checking based approach. And then, because it's quite obvious that uncertainty is relevant to this problem, I want to finish by talking about HAO star, which is an approach to reasoning about continuous resources that uses probabilistic modeling. And then at the end, I want to sort of wrap things up and make some comments about an iterative decomposition-based approach to progressing where we currently are in the community. So in this talk, you're going to hear some of the, I think it would be useful, I decided it would be useful to present you with some of the different alternative approaches that people have taken to this problem so that we can see what the state of the art is and we can see links between the various approaches and at the same time appreciate the different directions that people have come at the problem and what remains to be done to go further with this. So let me start with Kong-Ming, which was developed by Brian Williams and Hui Li. It's, as I said, a graph plan-based planner that's been developed for solving problems with continuous dynamics. And it works exactly as you would expect from a graph plan-based planner. Right? You build a plan graph out to a point where it looks as if the goals are achievable, and then you, in Kong-Ming, you take that plan graph and you encode it as a mixed integer linear programming problem, and you send it off to CPLEX to see if it can be solved. If it's solvable, then you're done. Otherwise, you extend the graph by one layer. Okay, so that's what they did, and they continue to do that until hopefully the problem is solved. And in their paper, which was published in ICAPS in 2008, they presented a little two-dimensional version of the AUV-type domain that I've just been talking about. Okay, so this is a simple situation in which you have just two dimensions, the horizontal direction and the vertical direction in which an AUV can travel in a cross-section of the ocean, and you have obstacles that have to be avoided. Okay, so here is the representation that they use. These are the continuous actions that are possible in that domain. Okay, the AUVs can glide, or they can ascend in the water, or they can descend in the water. Okay, and that's what you're seeing happening in this little image. They introduce, so this is like a PDDL type language, but it isn't PDDL 2.1 or PDDL plus, which I'll mention a bit later. This is their own language that introduces a new expressive component called the dynamics. Okay, and in the dynamics, you express basically the control dynamics of the problem. So when you glide, this represents how far the AUV moves in the x direction per unit of time. Right, so it moves between -10 and 10 distance units per units of time in the x direction, because it's gliding, so it's horizontal movement, and it doesn't move at all in the y direction, right? So because it's gliding, so it's not sinking or rising. Notice that the action is, although it's just called an action, it is in fact a durative action, and they have a duration d, which you'll see is the same in all of those actions. That's just, that's the simplest case. You could have different duration actions. They don't discuss that in their paper. Okay, so that's how far the AUV can move in the x direction per unit of time. And then when we ascend, then the AUV can move between -5 and -2 in the y direction per unit of time. And it also, notice, moves in the x direction, because when you ascend at an angle. And the same is true for descending. When you descend, you also move in the x direction. And then there are some discrete actions in this domain as well, because you can start and stop the rudder, and you can get a GPS signal, etc. Right? So a plan is going to consist of actions to glide, descend, ascend, take a GPS signal, start the rudder, etc. That's what a plan would look like, a mixture of these continuous dynamics actions and the discrete actions. Now, they introduce a representation for this continuous change, which they call flow tubes. And here's a very simple example on one variable. Right? So this is simply to give you the idea of what a flow tube is. Before an action is applied, there's an initial feasible region of positions or of values for this variable. Okay, so that's the initial feasible region. And then after the duration has passed while that action has been executing, that variable is now in a new feasible region, which you can calculate using the state equations. Okay, so the state equations tell you, in this case, it tells you that the minimum value for x after the duration d is equal to whatever it was before, plus the minimum movement of the vehicle in the x direction times the duration of the action. And then the maximum is calculated the same way. So what you're seeing is how you calculate the bounds on that variable as a result of an action continuing over a period of time. Right, so if you think about what a plan will look like, a continuous plan will look like, you chain these flow tubes together into a long sequence. And the way you do it is you've got an initial region of feasible states. So now our flow tubes are kind of multi-dimensional, because previously it was a one-variable example, and now obviously they could have many variables. In their example, they have two variables. But in any case, you start in an initial feasible region of states, and now you choose an action that's applicable in that feasible region. And it's applicable if its continuous precondition intersects with that feasible region. Right? If it does, then you take the intersection of the two, the precondition and the feasible region, and then you grow the flow tube from that intersection, which is called the resolved precondition. Okay, so then you've executed your action A for a period of time. That produces a new feasible region. Now you find an applicable action. You take the intersection, a new resolved precondition, another action gets applied, and so on. So that's how the flow tubes get chained together. And then a valid trajectory is any trajectory that passes through the allowed region of that flow tube, which is defined by the resolved preconditions. And any trajectory that does that doesn't leave the confines of the flow tubes, is a valid trajectory, even though you'll notice that third segment of that trajectory is a bit strange, because the dynamics are faster. That part of the trajectory is increasing faster than the flow tube suggests is possible. Right? But because that trajectory doesn't leave the legal bounds of the flow tube chain, it's considered valid. They could add additional constraints to say it's only valid if you stay following the allowed dynamics of the flow tube, but they don't do that. And it doesn't matter, it just means that they allow for more trajectories to be valid than would actually be valid at execution time. So how do they construct a hybrid plan? Well, this is the graph plan part of what they do, right? So you start in the initial state. Now, here's a key point. Even though they're talking about ranges of values of variables, there's no uncertainty in their situation at all, right? In the initial state, all of the continuous variables have known values, 0, say. Right, so in the AUV example, in the initial state, x and y are both 0, and then you've got values for the discrete propositions as well. Then you apply the actions that create the next fact level, and as you can see, you start the rudder, get the GPS, etc. There's one of the continuous actions being applied. Okay? When the continuous action is applied, it does this thing of fanning out from the initial region, which in this case is just a point, because the variables are 0. You fan out to the feasible region of states at the next fact layer. And that's marked there by the coordinate x, y is in the first region, which is that feasible region following the glide action. And now at the next layer, when you consider another continuous action, like gliding again or descending or something, then you would check that its preconditions intersected with that feasible region. You would take the resolved precondition, you'd extend out the graph. So this is graph plan, and therefore it has standard notion of graph plan concurrency. But of course, to have graph plan concurrency, you've got to have an appropriate mutex relation. So they had to extend the mutex relation to contain the continuous reasoning that's required, the continuous constraints that are required. So in particular, there's a mutex relation describing obstacle avoidance. So an AUV can't occupy the same space as is filled by an obstacle. And similarly, it can't be required to be in 2 different position ranges at once. You can't perform any action that would put it in 2 different position ranges at once, and so on. Those are the continuous mutexes that are required. And for details, you know, look at their paper, which describes all the details of how this is done. But this is enough to show you that they are basically building a continuous version of a plan graph, which they then translate into the MILP, try and solve it with Cplex. If it's not solvable, then they'll extend the graph by a layer in the usual way. Right, so what about their problem representation? Well, as I said, they introduced this PDDL-like syntax for modeling these problems. I just said there's no uncertainty. So why is there no uncertainty? It's because even though you are entering a feasible region of values for the variables after the application of an action, the assumption is that that's fully controllable, and that when you come to execute the trajectory, you can decide, or the controller can decide, which of the values it's actually going to take. And that's very important. It becomes very important later when I talk about the contrast between this approach and, for example, the HAO star approach. So we come back to that point, but it's important to bear it in mind. So given that there's no uncertainty, can we encode it in PDDL 2.1? Right? It doesn't immediately look like we could, because in PDDL 2.1 we don't have ranges, but of course these ranges are bounded by a min and a max, so we can, because those become the variables of interest in our PDDL 2.1 model. So let me show you this little simple example where you start with a variable equal to 0. You've got 2 actions, A and B. Right? The first action, A, the dynamics are that Vx, that's the distance moved in the x direction per unit of time, is between -1 and 1. So when you apply that action, you can use the state equations to calculate the bounds, and the bounds tell you that x is between -1 and 1 after the application of that action. Now you come along and you apply action B. That has as a precondition that x be between -0.5 and 0.5. So now to resolve that precondition, we find that subrange, which is the thick black bar, that's the resolved precondition, and we apply action B to that, and the dynamics are that we've moved between -2 and 2. So now we use the state equations again to calculate the new bounds, which are now between -2.5 and 2.5. Okay, so that's our little example that we're going to translate into PDDL 2.1. So here's how we would do it. We have durative actions. The duration is 1. And action A simply increases the maximum bound by #t and decreases the minimum bound by #t. And #t, as you know, is our notation for representing change per unit of time in PDDL 2.1 and PDDL+. Okay, so that's action A. Now, action B had this precondition that requires the variable to be in this smaller subrange. Okay, so the precondition defines a subrange, and the appropriate or the convenient mechanism for doing the resolution of the precondition is to say that we get start effects of the action, which is to resolve the precondition explicitly. So when we resolve the precondition, then we assign the max and min bounds to be the bounds that the precondition requires. And then we can go on and increase those bounds by the dynamics of that action. So it's not difficult to write that kind of controllable dynamics problem in PDDL 2.1. And in fact, PDDL 2.1 is more powerful than the dynamics language of Kong-Ming, because in PDDL 2.1 you can have these multiple concurrent updates on the same continuous variable, and in Kong-Ming you can't, because in the actions of Kong-Ming you have to specify the bounds. Right? So in Kong-Ming, although you can accumulate over a sequence, as we saw in the previous example, you can't do concurrent updates on the same continuous variable. Okay, so this is a slide that some of you will have seen before, because I often use it to try to make visible the difference between the discrete sort of semantics and the continuous one. When we move towards mixed discrete continuous systems, then we move away from this standard state transition semantics that we're used to, you know, that dates back to strips. And we introduce the idea of change taking place continuously over time, according to functions that are continuous, that affect the continuous variables of the problem. And even though my columns stop, just for the sort of sake of prettiness of the slide, of course, because time is going on forever, those columns stretch up along the time dimension. So what you see here is that you take discrete transitions between states, and then when you're in a state, continuous change changes the continuous variable values. Right? And we can capture all of that in PDDL 2.1 already with our durative actions and the fact that we allow duration-dependent effects. And we can transition by the choice of the planner into the states, and then we can allow the behaviors, the hash T-defined behaviors, to determine the movement up those columns. Right, so in the verification literature, there exists a model of hybrid automaton, which we used as the formal semantics for PDDL+, which I'm now about to look at. So the hybrid automaton has this notion of discrete changes between states triggering continuous change, which might then trigger some change into a new state that's determined by the world and not by the planning system. Okay, so you've now got the difference between the actions that the planner chooses and the events that the world chooses. And when an event transitions the system into a new state, time might pass and you might then choose to take another action which causes further continuous change, which triggers another world event, for example. And in PDDL+, which is the sort of successor of PDDL 2.1, we added these uncontrollable events and continuous processes to the model. That extends the durative action model to allow the world to take some decisions. And what you get is actions, processes, and events, which are all wrapped up in the durative action model of PDDL 2.1. Now, the reason I want to mention PDDL+ at this point is because that's the language that TML-PSAT uses for doing continuous planning. So TML-PSAT was the first planner to implement the PDDL+ semantics, which is effectively the hybrid automaton semantics, and use that as the basis for doing continuous planning. And it's an important piece of work as well, because there'd been a gap between the earlier planners that I mentioned, Xeno and Optop, and the appearance of another planner that was making more use of sort of modern technology to address these kinds of problems. TML-PSAT stands for Temporal Metric LP-SAT. Right? So it's not going to come as any surprise to learn that the core of this planner is Wolfman and Weld's LP-SAT system. So how does TML-PSAT work? Well, it takes a domain description in the problem and a horizon, which is the guest sort of horizon for the plan, and it translates all of that into a big CNF expression that captures not just the problem description, the domain, but also the PDDL+ semantics. Right, so you've got this huge CNF expression that adds in all the constraints that the PDDL+ semantics would enforce. And then that huge expression is sent off to this SAT-based arithmetic constraint solver, which consists of a SAT solver and an LP solver. Right? So that's the decomposition that you get inside the box. the SAT solver triggers linear constraints, right, that get sent off to the LP solver, and back come bounds, values, and inconsistency information. So basically, the LP solver tries to satisfy the linear constraints in the context of the SAT solution. If it can't be done, then it actually supplies some information in the form of minimal conflict sets, no goods, and so on, back to the SAT solver, and we go round the loop. And if there's a solution to all that, then it comes out and it gets decoded into a plan. And LPSAT, as I said, was the constraint solver. That box is basically LPSAT. But it doesn't have to be LPSAT, and they have another version which uses MathSat L4, which is Chamaty and Co.'s SAT-based linear solver. So there are various very interesting things about TM-LPSAT that I want to emphasize. One is the temporal ontology. Look at the top line first. Along the lines, along the arrows, is the continuous change, and the ovals represent the discrete happenings that transition between states. So notice that they define a vector of variables that they call T minus to stand for the values of the continuous variables immediately before the discrete happening. And then immediately after the discrete happening, you've got the same vector, but now it's T plus, right? And that means that the continuous change of the system is going on between T plus I and T minus I plus 1. Right? So if we look at this little schematic which comes out of a hybrid automaton, you can see that you step into a state, that's a happening. So you've got T plus I, that's your vector when you step into the state. And then time passes, which is the time between stepping in and stepping out. And over that time, you do the continuous change, and at the end, you've got T minus I plus 1. Okay, so that's the temporal ontology, and it's basically, as I said, because TM-LPSAT's implementing the semantics of PDDL+, you'd expect to find that relationship there. So in their compilation, what they have to do is build a whole bunch of constraints that express all of the ways that PDDL+ constrains a valid solution. So you've got to have, obviously, constraints for atomic actions, events, and processes. Then you also must have constraints for the triggering and termination of events and processes by continuous change. And this was one of the subtle things about the PDDL+ semantics. This is one of the things that we worked hard on making sure that worked right, because that's the bit that allows the world and the planner to cooperate together to find a solution, or rather allows the planner to understand what the world is doing so that a solution can be found. So validity of plans is absolutely critical. This condition is critical for validity of plans. And they also supply constraints for time point synchronicity and so on. So I'm going to come back to that triggering and termination issue, but first of all, let me show you an example of the sorts of constraints they construct. So this is the continuous constraints, right? So for every numeric fluent Q, and for any durative action or process that's changing that quantity over a period of time, right, they define a variable, which is called a gamma variable, that models the net change in that quantity due to that action or process over that period of time. Okay, so that variable models the net change due to a single action or process that's doing continuous change to that variable. But then, because there could be several of these happening concurrently, what they now do is they define this expression that says the quantity at the top of the tower of states, so T minus I plus 1, is equal to what it was at the bottom of the tower, so T plus I, plus the sum of all those gamma variables. And that's how they express the continuous updates on the same numeric variable. Now, plus, in the semantics, we introduced a special clock variable called time slip, which was intended to track the difference between the time when a triggering event, fact would become true, and the event or process that was activated by that got triggered. And of course, time slip should always be 0, because if it's anything other than 0, what you're saying is that the world waits for the planner to do things, and of course it never does. So time slip always must be 0. There must be no difference between a triggering fact happening and the event or process that gets triggered. Now, we introduced time slip because we wanted to work within the language of the hybrid automaton. There's a little bit sort of awkward in terms of actual implementation of that in a planner. But what TML-PSAT does is it just comes up with two variables, which are the time of the happening where the effect is produced and the time where the event triggers. So this is how they do it. Right, you're in a state, a happening occurs at this point, and that triggers this continuous process, and they say that those two must be equal. Okay, and then similarly, that process creates a happening when a critical value is reached that triggers some world event, and they say these must be equal. So it's a very neat way of making sure that there's no time slip between these critical things happening. Right, okay, so now for the bit of bad news, because TML-PSAT is a very innovative thing. I think it's a very interesting approach to managing this class of problems. The downside is that the compilation and compaction of the CNF expression is very expensive. So in their AIJ paper, they did comparisons with our old 2003 LPG system on non-continuous problems, so temporal benchmarks from the IPCs. And LPG was much faster and usually produced shorter plans, which, given that it was never optimized for any speed and it was always, you know, quite sort of comically slow, really, that shows that the CNF compilation compaction approach may not be very practical, but the intellectual contributions to that work are very important. And it has to be said, TML-PSAT solves a much larger class of problems in theory than LPGP does, because they can only compare with LPGP on non-continuous temporal problems, whereas in principle they can solve the continuous ones, as we've just seen. Right, let me just say a few words about Colin, which is the forward search-based planner that we developed within our group. So, you know, so far we've seen a graph plan-based thing, we've seen a SAT-based one, and now we're seeing a forward search-based approach. And I'm mentioning this one because later I'm going to come back to look at how this approach can be developed to the next stage. So what we have with Colin is a forward states-based search planner that builds on Crikey 3, which many of you will know is a temporal planner allowing required concurrency. And Colin, because it's built directly on top of Crikey 3, also manages required concurrency, which means in principle it can do those coordination activities that achieve the AUVs being in the same in their destinations at the same time point. Colin doesn't reason with processes and events, so it's not a PDDL plus planner, it's a PDDL 2.1 planner, but it handles duration-dependent effects, it handles numeric conditions and effects using increase and decrease for expressing these updates to continuous change. And of course, as we've seen, it allows for these multiple concurrent updates. In Colin, as it currently stands, all the continuous change is linear, but so it is in TML-PSAT and also in Kongming. Because the technology for solving numeric problems is becoming so good, it's feasible that we could replace the linear part of Colin, or any of those other systems, with a solver that solves a larger class of numeric problems, such as quadratics or maybe even other things, and expect that to be performing well. Now, TMLP's temporal ontology was like this, and Colin's is exactly the same. So I think this just draws attention to the fact that Colin and TML-PSAT are working on the same temporal semantics. And that's an important relationship between them. Because other people develop languages for modeling various kinds of temporal and continuous change, but they don't necessarily use the same semantics. They might have their own interpretation of exactly what's going on. I think it's helpful to the community if we can identify what is the underlying semantics that is behind the way this is modeled in this particular system, because then we can decide whether that is the semantics that we are also working to or want to change to or whatever for the sake of the kind of problems that we want to solve. Right, so how does Colin work? Well, in any state, it has a large linear program that contains all the temporal and linear constraints that are required by that state. And I want to show you just a little example of this. So the linear program is constructed by tracking the active continuous change on the variables. Right? So in the initial state, there's no active continuous change. So it's all 0 for all of the continuous variables. But as we start applying actions that add continuous change, then we sort of add that in, and as we end those actions, we take it out. And we've already seen how that's done. So let me show you this little example where an AUV is turning into position so that it can illuminate. And now let's suppose that there's a power curve involved, and when the AUV is turning, it's consuming power at the rate of 1.5 power units per unit of time. And when it starts illuminating, then that consumption gets increased by an additional 0.7 power units per unit of time. But when the turn stops, then we just have the 0.7 consumption coming from the illuminate. So that curve is changing according to how those actions interact. And in Colin, what we would do is we would say, right, we're in a certain state with a certain power level. We start the illumination. Because that's a discrete activity, it doesn't change the power level instantly. That gets changed over time according to the difference between the time when we entered that state and the time when we leave it, which, as you can see, I've marked there. There's 0.37 units of time between starting the illuminate and ending the turn. So that information is used to calculate the update to the power level, and now we add that constraint, set of constraints associated with that state. So what you're seeing here is a concrete example of how that continuous change is represented. Of course, once we're in a state, so we know how to build the linear program, we know that the linear program solver will be able to solve it. What I haven't yet explained is how we would compare one state with another, one Colin state with another, because we're in a forward search context, we want to have some kind of heuristic way of evaluating those. So what we do is we extend the temporal relaxed planning graph heuristic of Crikey 3, which I haven't got time to go into now, but it's a temporal extension of a relaxed planning graph that allows for the interleaving of concurrent activity. We're extending that in Colin to cope with the fact that when we evaluate a state, there might still be continuous change active on some of the variables in that state, and we don't know when that will stop. Right? So we don't have enough information to compute the initial layer of the relaxed planning graph. We've just got variables that are subject to continuous change. So what we need is some way that we can sort of fix up the initial layer of the planning graph so that we can then build an estimate. And what we do in Colin is we recognize that we're always in this situation, and there are certain constraints that we do know, such as the step out must be, the time of the step out must be greater than or equal to the time that we stepped in plus epsilon. So that plus epsilon, that matters, right? So you step in, a fraction of time goes by, you step out, and there must be at least that much time between the two. So that's a constraint. Plus we know, as we've already seen, how the values of the continuous variables at the top of the stack are constrained by the continuous activity that's going on whilst the time is passing. So we can say that the variables at the top of the stack are equal to what they were at the bottom, times the, plus the continuous change on those times the amount of time that's passed. And that's just a constraint that we know about. And we can use a linear solver to compute upper and lower bounds on those continuous variables that we can use for the construction of the relaxed planning graph. And once we're in the relaxed planning graph and we're building it out, obviously our actions have continuous effects. So we need a relaxation that allows us to manage that while, getting some benefit from the fact that there are effects going on, numeric effects going on, but not suffering from the complexity of reasoning about it. So the relaxation that we use is we say, okay, we're adding an action that has a continuous effect. Let's assume that we get all the benefit of that effect straight away and we can use it as soon as we like. And let's pretend that none of the negative effects occur. So it's like a delete relaxation or a sort of metric FF type relaxation. So we don't want to know about the bad effects, but all the good effects, we want those as quickly as possible. So that's our relaxation, and it gives us some reasonable search guidance for Colin. So just to kind of step back and give a more abstract look at what's going on, the architecture of Colin is you've got a forward search planner, and in every state, you've got a linear program containing temporal and numeric constraints. And that program gets sent off to a linear solver. In the current implementation of Colin, we're using LP-solve, but we will not be doing so for very much longer because most people are telling us that we really need to use something more powerful, something better. So that's what we'll be doing. But for the moment, that's what we've got in there. And here's something quite interesting. as I've just explained with the relaxed graph, if the linear constraint solver is happy with the linear program, then back come bounds for the construction of our relaxed planning graph. Okay? So that's what we get back in the case where the program is solvable. What do we get back in the case where it's not solvable? We don't get anything back. We just get pruning information back. Okay? So in other words, there may be information that could be exploited, minimal conflicts, etc., of the form that we were seeing in the LPSAT system. In our current version of Colin, we're not getting that, not exploiting that information. And the reason is because in a SAT-solving framework, it's well known, well understood how to incorporate that minimal conflict information, right? But in a forward-searching planner, it's a bit more difficult to do that well. So I'm going to come on to what we might do about that shortly. So what are the differences between what we're doing in Colin and what we've seen in the other approaches? Well, there's nothing new about the fact that Colin is using a linear solver, because everybody does that. Okay? Everyone's been doing that for ages as well, and not just in our community, but everywhere. So LPSAT, TMLPSAT, Kongming, SMT, all kinds of hybrid OR tools, all kinds of hybrid CSP tools, they're doing that. Right, but what I like to think of as the contributions of Colin is getting back to leveraging advances in our own community in planning, rather than saying, right, this could be coded up as a numeric problem and sent off to a solver from a different community. In other words, let's forget everything that we do in planning and just flatten this problem out into some other kind of thing and send it off to somebody else's solver. What we're trying to do in Colin, and I think this was also apparent in the early days of Zeno and Optop, but has kind of got lost, is to say we have huge advances in our own community. What we have to figure out is how we're going to leverage those to address these new classes of problems. Okay, so that's, it's first steps, but that's the direction that we're going in here. So whereas other approaches tend to use SAT solvers, model checkers, exhaustive search, etc., mixed integer linear programs as the main engine of solution of the problem, we're trying to use those as service technologies within something that builds on state-of-the-art. And we could extend our heuristic to incorporate advances in the development of propositional and metric heuristics that we've seen at this conference. Those could be incorporated into the temporal relaxed RPG. Right, now I want to describe UP Murphy, because many of you will be thinking, surely when you've got uncertainty in the problem, surely when you've got continuous consumption in the problem, there's some uncertainty that's going to arise. Surely these two are very closely related. And I want to come on to look at that, but UP Murphy provides a very nice bridge to understand, where that uncertainty is. So UP Murphy uses model checking to synthesize these universal plans, which we might call policies, right, for hybrid plant. And they are not working directly, explicitly with the uncertainty in the system. They are working at a higher level of abstraction where that is not their main focus. And I'll show you how they take that into account. So the approach also is novel, right? Very different from everything we've seen so far. It works by iterative refinement of an initially coarse discretization of the problem. Right? So basically you start with a very coarse discretization, you solve that, you see whether it works with respect to the original continuous problem, and if it doesn't, then you refine the discretization. And that's very nice, right? Because it allows you to get the full benefit of discretization and all the power you get by making the problem much, much simpler, but you validate it with respect to the original continuous problem, and that's your guide for the refinement, the level of refinement you need to reach. Okay, so remember Kongming, right? This is how Kongming works. You're in some feasible set of states. You apply some action that leads you to a feasible region of states, and all this is continuous, yeah? Then you've got some precondition of some action that's applicable in that feasible region, and you resolve its precondition, and then you apply the next action. And that's how you get this chaining of flow tubes, right? Now, what would UP Murphy do with this problem? Here's the AUV problem, okay, with the continuous actions, glide, ascend, and descend. What UP Murphy will do is it will start with a coarse discretization. Now that discretization might be done just by taking the bounds of the ranges as the only possible values of the variables. Okay, now if you do that, it's very coarse, obviously, much coarser than they would actually do, but for the sake of our example, let's say they do something this coarse. You take that, you then get a collection of instances of the continuous variables that are, of the continuous actions that are now bound to those particular values. And because the Vx and the Vy values allow you to infer the x and y, you get a discretization of the positions of the vehicles as well. So now the whole problem is discrete. So they've discretized. Now the next step is to explore the state space under that discretization. So this is their kind of discretized flow tube thing that they would build. Now what do? They synthesize a first guess at a policy, a controller table, based on the state action pairs in that discretized flow tube, let's call it, because I want to make the comparison with Kongming. Now, that obviously, that's a policy, but it will not be powerful enough to control the controller because there'll be too many state action pairs missing. So now they do something very interesting. They say, right, you know, there are not enough states in here, we're going to reach other states, but let's suppose that if we perturb those states and actions, that we'll enrich the collection of state action pairs enough to make the controller workable. So they do this bit of perturbation, which they call robustifying, right? And they add the extra state action pairs to the controller table. Now, what's nice about that is that they're robustifying, they're kind of juddering the states and the actions to give you a little bit more flexibility about what you apply and where you get to. But they recognize that if you just do that mindlessly, then probably you'll be adding useless state action pairs. You won't actually reach the states that you added in. So instead of doing that, they use a probability distribution to tell them what are the safe states, the ones they're most likely to reach if they progress from one state to another. And these are the ones that they add to the controller table. And when they've done that, they compress the controller table into a compact representation, which is an OBDD representation, and then they validate it against the continuous dynamics of the problem. And if it's a solution, great, they're done. And if not, then they refine the discretization. And if they have to do that, then they'll explore more states. And maybe they have to refine it again, they'll explore more states. So the nice thing about this approach, I think, is that you start out with a discretization that, you know, I gave a very, very trivial example. They would start with something that you had some reason to believe might actually be useful, because they don't want to just do thousands of iterations if they can get away with fewer. So even their coarse discretizations are quite rich. But the principle is you start with a coarse discretization and then you gradually refine that until such time as you've got enough of the problem, especially with this random perturbation, you've got enough of the problem in there that you can get a valid solution to within some tolerance of what would be acceptable if you were you know, working with the continuous dynamics. So that's their architecture. You guess a discretization, you do the planning process I just described, you go off to a validator to see if it's valid. If it is, you're done. Otherwise, you refine the discretization, you go round. Right, so here's the link with the probabilistic stuff. Oh God, I've gone on too long, I'm sorry. I'm wrapping up almost. Here's the link with the probabilistic stuff is that you've got this robustification, which is based on probability distributions, and that allows me to quickly mention an approach that's based on Markov decision processes. So if you're in a Markov decision process situation, then when you take an action, you get probabilistic outcomes. Right? What they've done in HAO star is to say when you take an action, you also get uncertain resource consumption, which they model by a probability distribution over the amounts of resource that you might have consumed. And the consequences of that is that you've got a hybrid state. Right? Now, if you've got a hybrid state, then the standard value iteration approaches don't work, and they've developed a hybrid algorithm for finding best feasible policies under the resource constraints that exist. Right, there's no controllability of resource. Okay, so here's a big contrast with Kongming. All the resource components of the problem are uncontrollable. If you were to represent this resource consumption in Kongming, Kongming would do it by saying we can move these many resource consumption units in this resource direction, right, leading to a feasible region of state, but now we have complete controllability over which one of those we'll actually access when we apply the action. Right, so Kongming would do a controllable version of what's going on here. Right, so here's the contrast. Kongming's action leads to a feasible region, which is continuous range of values, reachable under hybrid control, and the action is controllable. Whereas in HAO star, if we drew it the same way, the action would have uncertain resource requirements, and the feasible region would be a continuous distribution over the resource values, and the resource is uncontrollable. What about if we combined the two? So this just occurs because it occurs to me because it's a natural thing to try to do. Because in Kongming, you would say, here's the resolved precondition. That's going to be where I apply my next action. Right? But if you were to always find that your resolved precondition sat right on the edge of the feasible region, and that happened all the way along the trajectory, then the resulting trajectory would be very fragile. So what about if instead you were to say, right, here's the action, again a Kongming action, controllable effects, there's the feasible region, but actually there's a sub-range of that feasible region, which is the most likely collection of values. So what we'll do is, this is like UP Murphy's safe states idea. You've identified those ones that you're most likely to reach because they're the ones that are going to be most useful for progression. Then you resolve the precondition, the next precondition against that sub-range of most likely or safest, most robust choices, and you're going to get hopefully a trajectory that lies in the middle of the flow tubes instead of right on the fringe of it. So if we bring the ideas together, then we have a standard technique. The standard technique is to decompose into the discrete and the continuous. Sometimes people just hand the whole thing off to something from the OR community that does that decomposition for us. Sometimes we break it down ourselves into the bit we can SAT solve and the bit that we require the LP solver for. What we're seeing in HAO star, because it's building on MDP advances, and in Colin, and in the early planners, Xeno and Optop, what we're seeing is something that's trying to get the benefits of the planning advances that are available at the time of development of the work. So what comes next? Right. This is something that has it seems particularly relevant to the development of these kinds of planners. It's the classic Bender's decomposition technique from the OR literature. And I'm going to give you the briefest introduction to what this is. You start with a mixed discrete continuous problem, which is expressed as a function that has to be minimized or maximized, subject to some collection of discrete and continuous constraints. The first step is to find a continuous subproblem, separate out the discrete and the continuous. So far, so standard, because that's what everyone does. But in the classic Bender's decomposition, you then form the dual of that subproblem. And we're not going into details here, but the dual has the nice property that whether the original subproblem is solvable or not, you get information from the dual. If the original subproblem is feasible, then you get optimality cuts from the dual. You can extract optimality cuts. And if it's infeasible, then you can extract feasibility cuts. Okay, so that's the idea. And then you feed that information into your master solver, which is solving the discrete part of the problem, and you keep going around this. Right, why is that different from, let's say, going around a SAT-LP process and using minimal conflict sets? What's different is that the Bender's decomposition has various properties that can make guarantees about the type of information that's coming back, and you're not using greedy approaches for selecting the minimal conflicts or other ad hoc approaches for extracting whatever information you can quickly extract from the process. You're getting very specific information back from here, and in fact the information is specific enough that Bender's decomposition can guarantee convergence on optimal solutions. Even if you're a discrete planner that you're using in there, let's say it's a planning problem, even if that's not an optimal planner, if you had the time to wait, then Bender's decomposition would be able to find you an optimal solution to your planning problem, which is quite neat, considering you started with some non-optimal strategy. So quickly to give some intuitions, if you're in a situation, the coloured lines here, try and show you which coloured lines I'm talking about. These ones, right? They are constraints of the problem that mark out this polygon where solutions lie. And let's suppose we relax the problem so that you've got integer and non-integer solutions in there. Then what you really want to do is you want to squeeze that polygon so it only contains, so it restricts you to the optimal integer solutions that you're interested in. Okay, so what you really want to do is to cut away that star up there is an optimal non-integer solution, and you want to get rid of it. So a cut will get rid of that. And what you're doing with these cuts is squeezing that polygon so that it contains only the solutions you want. And in a planning situation, you would start with a master discrete solver that would propose the logical causal structure of a plan. A subsolver would then say, okay, what can we do with this? Right? And it might return some feasibility information that says that plan's no good because there's not enough resource to do all the things you want to do in it. That feasibility cut would then be used by the master solver to come up with a new solution to the problem, which now the subsolver says, keep these things the same. Okay? Keep these values the same, because you've got a feasible solution here, but it's not optimal. Keep these things the same and try and do a better job of the rest of it. And then it goes round and round the cycle. So if we remember how Colin works, that's the current situation. What we would like to do is to pass our linear programs into this box, go through the Bender's decomposition. In the case where the dual is infeasible, then we're going to get, well, this is a bit technical, and obviously I can't go into it. We're going to get information that allows us to extract feasibility cuts, which now we have to decide how we're going to use that in the forward chaining framework. But one thing we might do, if the feasibility cut told us that there wasn't enough resource for us to do all the things we wanted to do, then we might add some prefix resource production actions to allow the state to be considered a valid state on the path to a solution. Optimality cuts are more difficult because you really need to do some kind of plan repair if you get optimality cuts back. It's not clear to us yet exactly how to integrate that into Colin, but that's the direction that we're going in. So this is my last slide, and I just want to remind you what we came in with. So we have these mixed discrete continuous problems, lots of AUVs operating in an ocean environment, lots of other assets. This is the type of plan where all of these assets are kind of choreographed to achieve the task of maximizing science return. Lots of temporal coordination, lots of reasoning about how to solve the numeric aspects of the problem. And that's a benchmark, and that will shortly be available as a PDDL 2.1 or even PDDL plus benchmark for people to experiment with. Thank you very much.
Thank you, Maria, for this very interesting talk and survey of various approaches. I have two questions. One is with respect to the double ontology, both the one of Colin and I understand that time flows both in the continuous area and also in the discrete transitions. So you have time flowing in the two.
No, so the discrete transitions are instantaneous.
They are instantaneous.
Yes.
So you put all your duration on
in the temporal dimension, yes. Okay. And that's because the instantaneous change, you should see that as just the start of application of an action that causes continuous change. So nothing is happening on that discrete transition other than that you enter a state where continuous change is passing.
Well, in some hybrid modeling, you may also need to consider durations of the discrete change. This is discrete with respect to the triggering, and then you end up somewhere without necessarily a continuous transition.
Right, so in the semantic model that we developed for PDDL+, and there's the reduced version of that works for PDDL 2.1, we were following the hybrid automaton semantics. So it may be that we want to enrich that semantics in various ways, as you've said, if we want additional modeling power. But that's the current semantics of the language.
And my second question is that in the continuous area of your modeling, you might consider planning with respect to the control parameters.
Yeah.
Planning in control theory means usually using dynamic programming. What are the
Well, so that's a very interesting question, because I think there are two ways you could do it. You could either do an integration so that you're saying, let's treat part of the control problem as a planning problem, or you could say, well, actually, the controller is there underlying whatever we've got, because when we've produced a plan, we're going to need a controller to execute it, and at that level, the controller will do what it does in those terms. We don't want to actually raise that to the level of planning. And I think the approach that we've taken is to say we are trying to get the maximum out of abstracting the problem to the causal structure of the problem, where we cope with the combinatorial choice and we take into account as much as is required to avoid having to make harsh conservative estimates about how long things take, etc. But when it comes down to actual execution, it will be a controller that decides eventually how to interpret those actions. And I think that's the level where that kind of reasoning would be done.
You mentioned to apply Bentley's decomposition, and what I remember from that is that the theoretical point of view is a tremendous nice approach. However, what I remember is that convergence in terms of the number of constraints of Bentley's cuts in that principle is the major problem. Yeah. What makes you believe that it is applicable in your situation?
Right. Well, I don't believe that we can ever wait long enough for to benefit from the actual convergence on an optimal solution. So I think that's very unlikely. However, I think that the fact that the approach has those properties means that we would expect the information we're getting back on each iteration to be somehow richer than we would get if we were just doing a greedy search over different kinds of constraints that we might add to our representation. So I think what we're hoping is that with judicious use of the approach, that we'll benefit from those properties without actually ever realistically expecting to converge on optimal solutions. That's really what we're hoping. But I agree with you. I mean, this is the major problem with actually implementing and expecting to see those kind of gains in reality. But I think
what you're aiming for is the quality of the Bentley's cuts.
Yeah. So right. So what we're heading for is a way of integrating that information that's coming back from the numeric solver into a forward chaining planner that is, you know, a good, powerful integration, where the information that's coming back is the kind of information we can use to enhance the quality of the plans that we're producing and also hopefully make us arrive at good quality solutions more quickly. But some of those aspects of what do you mean by good, etc., that's still to be determined as we progress with this.
Thank you.
Are you looking at or considering using motion planners for doing some of that sort of feasibility checking instead of LP solvers?
Yeah. So as I mentioned at the beginning, you'd be crazy to try and do the motion planning as part of the task planning because the level of reasoning is completely different. So what we would like to do is to figure out how to do that integration. And that's why I went to that workshop, because I was thinking, you know, there is a community of people now looking at the relationship between motion and task planning, and I think that interest will grow. So yes, I mean, absolutely, I'm a great believer in using what exists for the role that we need done within our planning framework. But I want the main framework, the main engine to be a planner using all of the advances that we've made in the planning architecture and using these other techniques as we need them rather than reinventing the wheel. So definitely be very keen to do that.